In this lecture, we'll be taking a look at both the processes of internal and also external respiration. To start here, I just want to remind you about some topics that, or at least some concepts that I've presented to you before. And first up, that is the fact that respiration, obviously, once again, is an exchange of gases. Therefore, external and also internal respiration represent exchange of gases. You should keep in mind the two locations that the gases are being exchanged between during each process. During the process of external respiration, we're going to see an exchange of gases between the air within the alveolus and the blood flowing through pulmonary capillaries. During the process of internal respiration, we're going to see an exchange of gases between the blood flowing through systemic capillaries as well as the tissues that are located throughout the various organ systems. So there's two distinctive locations via which blood is being exchanged during each process. Now, we consider this process of gas exchange, respiration. It occurs via a principle that you've heard of before, going back to general biology. That principle is called diffusion. Quite simply put, when gases are exchanged, they diffuse. So oxygen must diffuse from one location to another, and carbon dioxide will also diffuse from one location to another. Now, when you consider diffusion, or at least if you recall, diffusion is typically defined, at least in diffusion is typically defined within general biology as being movement of a molecule from an area of higher to lower concentration. Well, with that being the case, we now need to start to try and rephrase or redefine diffusion as it relates to gases. Enter now a new gas law referred to as Henry's law. And Henry's law redefines at least redefines for us what is referred to as a concentration of gases. When it comes to gases, we actually don't use the term concentration. According to Henry's law, if you look at a mixture of gases such as the atmosphere, each gas is going to move or behave independently of the others. So, technically speaking, Henry's law says that when you have a mixture of gases, each gas exerts its own independent partial pressure within that mixture of gases. So, if you recall, we've talked about atmospheric pressure before, at least mentioned it. Atmospheric pressure at sea level is roughly 760 millimeters of mercury. Well, if you look at it, oxygen makes up roughly about almost 21% of that 760. So if you do the math, the partial pressure of oxygen within the atmospheric air is around 159 millimeters of mercury. That means that oxygen doesn't necessarily care what carbon dioxide is doing, carbon dioxide doesn't care what nitrogen is doing, and so forth on down the line. So essentially, each gas has its own individual pressure, once again referred to as a partial pressure. Well, Henry's law lets us expand into the next law, which is called Dalton's law. And Dalton's law specifically defines for us, or at least gives us principles as it relates to the diffusion of gases. So here we go. With Dalton's law, it's rephrased, at least diffusion, from being the movement of from an area of higher concentration to a lower concentration to being movement of a gas from an area of higher partial pressure to lower partial pressure. The first part of Dalton's law essentially states that you must have a partial pressure gradient in order for a gas to diffuse. Now, I'm going to use the numbers here on this diagram to show you how this works. However, for the purposes of your test, you do not have to know any numbers. What you should work at is being able to set the partial pressure gradient up in the correct direction. So if you take a look here during external respiration, we've already said that oxygen must go from the alveolus and in the blood. So according to the first part of Dalton's law, we need to have a higher partial pressure of oxygen within the alveolus and a lower partial pressure of oxygen within the blood, and therefore oxygen will move from where the partial pressure is higher to where the partial pressure is lower, and it will diffuse from the alveolus and into blood. Like I said, the numbers just confirm that for you. Take a look here at the partial pressure of oxygen within the alveolar air. It's roughly 105 millimeters of mercury. If we take a look at the partial pressure of oxygen in the deoxygenated blood, which is flowing into those pulmonary capillaries, it's 40. 105 is greater than 40. Oxygen goes from the higher partial pressure to the lower partial pressure, and oxygen would diffuse in the blood. Exactly what we said should happen during external respiration. We'll see the same scenario of movement play out from higher to lower partial pressure when it comes to carbon dioxide, but in the reverse direction. If we look at the partial pressure of carbon dioxide in deoxygenated blood, it's going to be around 45 millimeters of mercury. However, if we look at the partial pressure of carbon dioxide in alveolar air, it's around 40. Once again, carbon dioxide is going to go from where the partial pressure is higher to where the partial pressure is lower, and ultimately enter the alveolus, and it will be exhaled out. So, once again, you don't have to tell me any numbers, but you absolutely have to be able to set up that partial pressure gradient in the correct direction. Suffice it to say, you should be able to tell me this. During the process of external respiration, the partial pressure of oxygen is higher in the alveolar air, and it's lower in the pulmonary capillary, or in blood. Also, the partial pressure of carbon dioxide will be greater in blood, or in the pulmonary capillary, than it is in the alveolar air during the process of external respiration. Essentially, like I said, you just have to be able to tell me where the partial pressure is higher and where it's lower. In other words, set up the partial pressure gradient correctly. Now, when we start to take a look at the process of internal respiration, it's going to be a similar scenario. Once again, we're going to have diffusion occurring, but now we're going to have blood diffusing from the systemic capillaries, or we're going to have, oxygen diffusing from the systemic capillaries or blood and into the tissues. So the higher partial pressure of oxygen has to be within blood, the lower partial pressure of oxygen here within the tissues, and we get the correct direction of movement. You can see the numbers once again confirmed. The partial pressure of oxygen in oxygenated blood is going to be 100. Partial pressure of oxygen within the systemic tissues around 40. Oxygen will move from high partial pressure to low partial pressure and enter the tissue. Just the opposite direction of movement when it comes to the carbon dioxide. Higher partial pressure of carbon dioxide is going to be here within the tissues. Lower partial pressure of carbon dioxide is here within the blood, and we get carbon dioxide movement from higher partial pressure within the tissue to lower partial pressure within the blood. So that is kind of a summary here of the first principle involved with Dalton's law. Essentially, remember, the first principle says that you must have a partial pressure gradient. If you don't have a partial pressure gradient, in other words, if you don't have a higher partial pressure in one location and a lower partial pressure in the other, you will not get diffusion. Next, we need to consider the second part of Dalton's law. And the second part of Dalton's law involves solubility concepts. Obviously, as we just said, you must have a higher partial pressure and a lower partial pressure in one location or another in order to get diffusion. But the second part of Dalton's law says you must also have that gas be soluble in the media that it's diffusing into. Now consider the processes that we're discussing here. External and also internal respiration. You've got two different media involved, two different states. You got one, a gaseous state, the air, as it would be the case if you were in the alveolus, and the other state is liquid, in other words, blood. So we've got both a liquid state or liquid media and also a gaseous media involved in this exchange process. Well, the reality is the solubility principles are not the same in both the gaseous state and also the liquid state. If we consider a gas diffusing into another collection of gases, that gas is typically going to be readily soluble. But when we start to consider a gas diffusing into a liquid like blood, which is mainly water, well, the solubility, it may be a little bit different. And that's exactly the case. So, if we consider here in the second diagram, you can see the oxygen going from the alveolus into blood, the carbon dioxide here going from the blood into the alveolus. But this diagram specifically relates to the second part of Dalton's law and the solubility. The reality is blood, which is mainly composed of water, is not highly soluble for most gases. So, in other words, we're going to need a workaround essentially to try and get around the fact that oxygen and carbon dioxide are not readily soluble in blood. So, in this discussion, we're going to take a look at how oxygen is transported and also how carbon dioxide is transported. And we'll begin with oxygen transport within the human body. If you take a look up top at the right hand side of the diagram, you'll see the two major ways in which oxygen is transported. 1.5% of oxygen is going to be directly dissolved in plasma. Now, like I said, oxygen is not readily soluble in blood. I didn't say it couldn't dissolve at all. So about 1.5% of your total oxygen is going to be dissolved in plasma. So that leaves 98.5%. The other 98.5% will be bound to hemoglobin. When oxygen is bound to hemoglobin, it's referred to as oxyhemoglobin. So 98.5% of your oxygen is carried as oxyhemoglobin. Well, the reality is, it's great that oxygen can be bound to hemoglobin, but if we consider the process of internal respiration, that oxyhemoglobin also needs to be able to release oxygen. This is a principle called reversible binding. If you look in your text, all reversible binding refers to is the fact that at some point hemoglobin binds oxygen, and at another point it will release it. It reversibly binds it. With all that being said, we have to consider the chemical influences that will ultimately allow hemoglobin to bind and also release oxygen. And I'm going to give you 4 chemical influences here. Now, your book will go through a much lengthier discussion, but for the purposes of this recording, I'll try to keep it as straightforward as possible. What you have in front of you is called an oxygen dissociation curve. Across the x-axis, you'll see the partial pressure of oxygen, and over here on the y-axis, you've got the percent saturation of hemoglobin. The percent saturation of hemoglobin is a reflection of how much hemoglobin actually wants oxygen. How much hemoglobin actually wants oxygen is a concept that we refer to as hemoglobin's affinity for oxygen. If hemoglobin has a great affinity for oxygen, it means that it wants the oxygen. So when we have a higher affinity for oxygen, at least in relationship to hemoglobin, we'd expect our percent saturation to be closer to 100%. Why? Because hemoglobin wants oxygen and it will bind it. However, if that affinity should change, in other words, if the affinity that hemoglobin has for oxygen should decrease, we would expect our percent saturation to be lower. We'd expect the percent saturation to be lower because essentially hemoglobin doesn't want oxygen if its affinity for oxygen is going to be low. So we're talking about a concept, once again, coming from your text that's referred to as affinity for oxygen. Hemoglobin's affinity for oxygen will change. In some cases, hemoglobin's affinity for oxygen will be very high. If that's the case, hemoglobin will bind oxygen. When that affinity changes and it lowers, hemoglobin's affinity for oxygen will decrease and it will release that oxygen, hence leading to reversible binding. So let's talk about the chemical influences that change hemoglobin's affinity for oxygen. The first of those is the partial pressure of oxygen. It is the most dominant chemical influence that will influence that affinity. As the partial pressure of oxygen changes, so does the hemoglobin affinity for oxygen. In other words, the partial pressure of oxygen is directly related to hemoglobin's affinity for oxygen. However you change however the partial pressure of oxygen changes, so too will the hemoglobin affinity for oxygen change in a similar manner. Let's take a look at this oxygen dissociation curve and talk about how that happens. If you look here, you got a partial pressure of oxygen around 100. In other words, a very high partial pressure. Partial pressures of oxygen like this in the human body are typically only seen in places like the lungs. When you have that elevated partial pressure, you can notice that the percent saturation is upwards around 100. So when the partial pressure of oxygen is high, we get 100% saturation, indicating that our affinity should also be high as well. But as you move toward the left-hand side and the partial pressure of oxygen decreases, look at what ultimately happens here to the percent saturation. The percent saturation also begins to fall as well. Well, this isn't such a bad thing because within the human body, the PO2 within the tissues or at the systemic level is going to be lowered. So when that PO2 decreases, it would ultimately indicate a need to release the oxygen. So as the PO2 decreases, hemoglobin's affinity for oxygen will also decrease. So that's kind of how this chemical influence relates to partial pressure of oxygen works. The PO2 changes, and in the same manner, hemoglobin's affinity for oxygen will change. And as that affinity changes, you will bind and also release oxygen. Now, the other 3 chemical influences that I'm going to give you are summarized in 3 separate oxygen dissociation curves, but I'm going to combine them into one concept. First, we'll consider the amount of acid. Notice I'm specifically saying the amount of acid instead of saying pH. My way to remember this does not work if you use pH. So think amount of acid, also the partial pressure of carbon dioxide, and also heat or temperature. So we're considering the effects that acid, the partial pressure of carbon dioxide, and also heat or temperature would have on affinity. Now if you consider all 3 of those, temperature, partial pressure of carbon dioxide, and also acid, they have one commonality between the 3. They're all metabolic waste products. And what they indicate when they're present in greater amounts is that you've got a higher rate of metabolism. When you're using up more energy, you're going to produce more carbon dioxide because your cells are going to carry out greater amounts of aerobic respiration. You're also going to have more chemical reactions occurring, so you're going to give off more heat. And you run the possibility of generating acid as lactic acid is produced. So increasing amounts of acid, elevated levels of PCO2, and also increased amounts of heat all indicate a rise in metabolism. If the metabolism rises, what will also increase is the need that the tissues have for oxygen. So if you look at it, higher amounts of acid, higher temperature, and also higher PCO2s will all decrease affinity for oxygen. So these last three actually have an inverse relationship with affinity. As you increase partial pressure of carbon dioxide, as you increase the amount of acid, or as you increase the amount of heat or temperature, you will see a decrease in hemoglobin's affinity for oxygen. So keep in mind definitely the four chemical influences: PO2, PCO2, heat, and also the amount of acid. Remember how each will influence that affinity, and also keep in mind that concept there of reversible binding. Now there's obviously also another gas involved in these processes, and that's going to be carbon dioxide. Carbon dioxide also has a story. You can see 7% of carbon dioxide is transported simply as dissolved carbon dioxide. Another 23% of carbon dioxide is actually bound to globin. The globin, remember, is the protein component of hemoglobin. When hemoglobin is bound to carbon dioxide, we call it carbamino or carboxyhemoglobin. You should see those terms in your text. However, 70% of your carbon dioxide is transported as an ion called bicarbonate. And bicarbonate is very critical to the body because it helps buffer the pH of various body solutions. Remember, once again, the average pH of the body is 7.35 to 7.45. These buffers help prevent rapid swings in pH so that the pH doesn't become too disrupted and therefore fall outside of homeostatic range. So these buffers are very important. However, when it comes down to an exchange of gases, bicarbonate is not a gas. The gas that's exchanged is carbon dioxide. So quite simply put, when we start to consider the fact that 70% of carbon dioxide is transported as bicarbonate ions, you're going to have to convert it. And the equation I'm about to show you next is a very critical one that you'll see over and over the next couple of chapters. When you look at carbon dioxide, which is produced by the tissues, it must be converted ultimately into a bicarbonate ion. In order to do so, this all plays out inside of a red blood cell. The red blood cells will take carbon dioxide and combine carbon dioxide with water. In order to make this reaction occur, an enzyme is needed. That enzyme is called carbonic anhydrase. So the first step in the conversion is for carbonic anhydrase to take carbon dioxide and water and convert it into carbonic acid. Once we have carbonic acid, well, nature will take over. Carbonic acid belongs to a collection of acids in nature known as weak acids. Weak acids have the ability to either fall apart and give you acid and the corresponding salt, or they can spontaneously come together to give you the acid form. It just all depends on the solution that they're in and what's being dictated by that solution. Well, in this case, as carbonic anhydrase assembles carbon dioxide and water and gives us carbonic acid, because we would have rising amounts of carbonic acid, the solution is going to cause carbonic acid to simply fall apart and give us acid, and there's our bicarbonate ion. The acid is usually accounted for by hemoglobin. Hemoglobin typically can buffer the internal solution of a red blood cell. And the bicarbonate, well, remember, that's how 70% of our carbon dioxide will be transported. So that's how the conversion works. It's a two-step process. In the first part of the process, we take carbon dioxide and water. Carbonic anhydrase will unite those two in order to form carbonic acid. The second step, carbonic acid will simply fall apart and give you acid plus a bicarbonate ion. The bicarbonate gets released into the blood and carried around, and then the acid is united with hemoglobin in order to prevent the pH of the red blood cells from becoming too acidic. Now, it's great that we can take and convert that carbon dioxide into bicarbonate. But when we reach the lungs for external respiration, well, you can't exhale bicarbonate. So you have to convert it back into carbon dioxide. So what happens within external respiration is that these reactions run in the opposite direction. So during internal respiration, these reactions go from your left to your right. But for external respiration, they actually go from your right backwards to your left. That's why you have these double arrows in between each reaction. Double arrows within chemistry mean that the reaction can go in either direction. So, during external respiration, the bicarbonate, as it flows through the pulmonary capillaries, will be picked up by red blood cells. Those red blood cells then use some of the acid that hemoglobin was bound to, and they unite the acid with the bicarbonate to give you carbonic acid again. And in this situation, as the carbonic acid increases, carbonic anhydrase will take carbonic acid and break it apart to give you water and your carbon dioxide again. And now you can exhale the carbon dioxide. So, carbon dioxide transport, it really comes down to three ways. There's dissolved carbon dioxide. Not much to say about that because it's directly dissolved. It's already in a gaseous form, so you don't have to do any conversions or anything special. Then there's carbamino or carboxyhemoglobin. That's when carbon dioxide is bound to hemoglobin. There are triggers that influence the binding or release of carbon dioxide, and really it's all about hemoglobin's affinity for oxygen. If hemoglobin wants oxygen, it'll kick off carbon dioxide and bind up the oxygen. However, if hemoglobin's affinity for oxygen changes and it doesn't want oxygen, it'll kick off the oxygen and pick up carbon dioxide. So it depends on which way you're going. And then you got those bicarbonate ions. Remember, they're useful because they help buffer the body's pH. But basically you have to take carbon dioxide that's produced by the tissues and convert it into bicarbonate. So during internal respiration, the reactions you see on the screen in front of you go from the left to the right. And then once you reach the lungs, during external respiration, you have to convert bicarbonate ions back into carbon dioxide. And in that situation, the reactions you see on the screen will go from the right to the left. So that's the story of carbon dioxide transport throughout the body. Definitely remember the three ways, and we're about to get into the kind of final push here with external and also internal respiration. And that final push is meant to try and help you understand what's happening in these two diagrams. These two diagrams are an application of everything we've talked about to this point. They pull in the whole concept of partial pressure gradients, where the gases are being exchanged between, the conversions, everything. So I'll walk you through them, but hopefully after going through the reading, you kind of can walk yourself through these as well. We'll deal first with the process of external respiration. You should recall that external respiration is an exchange of gases between the air within the alveolus and blood. So there's remembering where the gases are being exchanged between. That's that part. Well, next you would need to know the direction in which the gases are moving. So we have the oxygen moving from the alveolus in the blood, then the carbon dioxide moving from the blood into the alveolus. Once again, this is a stepwise procedure, so you need to know where the gases are being exchanged between, and then you need to know in which direction the gases are moving. Next, let's apply the partial pressure gradient. Well, we know that we have to go from higher partial pressure to lower partial pressure. So during external respiration, the higher partial pressure of oxygen is within the alveolus, and the lower partial pressure is here within blood. That's the only way we can get this direction of movement. And if we consider carbon dioxide during external respiration, the higher partial pressure of carbon dioxide must be within the blood, and the lower partial pressure within the alveolus. That is how we'll get the correct direction of carbon dioxide movement, and ultimately that carbon dioxide will be exhaled out. Now, when we start to look at the movement of the gases, or rather where the gases exist, we just have to tell a story. Tell the story of how each gas is moved. So let's consider oxygen. As oxygen goes down its partial pressure gradient and enters blood, well, 1.5% of that oxygen will just simply stay dissolved in plasma, which is a part of blood. The other 98.5% diffuses into red blood cells, where hemoglobin will bind it. Now, why will hemoglobin bind oxygen during external respiration? Remember, when the partial pressure of oxygen, the PO2, is high, that's when hemoglobin's affinity for oxygen will be high. And I said earlier, the highest partial pressures of oxygen occur within the lungs, and that's exactly where this process of external respiration is taking place. So during external respiration, hemoglobin's affinity for oxygen is very high. So anything that hemoglobin may be holding on to, like a hydrogen ion or carbon dioxide, will be released and given off. And when that release occurs, the hemoglobin is now free to bind up oxygen. becoming oxyhemoglobin. So this is all about affinity. Hemoglobin binds the oxygen because its affinity will be high because the PO2 is high. And that's oxygen's story during external respiration. Now let's tell carbon dioxide's story. Well, account for each way that carbon dioxide is transported. So 7% of your carbon dioxide is simply dissolved. You don't have to do anything to it. You don't have to change it. It's already carbon dioxide. So it simply goes down that partial pressure gradient, enters the alveolus, and is exhaled out. You're done with that form. Next, we have carbamino, or carboxyhemoglobin. Well, remember what's happening here. Hemoglobin doesn't want carbon dioxide. It wants oxygen. Why? Because the PO2 is elevated. So hemoglobin is going to kick off the carbon dioxide, free it up, and now this freed carbon dioxide can just simply continue to move and occupy the space, or the percentage that was left, that was opened up, if you will, when the carbon dioxide that was dissolved moved out into the alveolus. So essentially it's kind of like a supply chain. You can move some of that carbon dioxide out, and that lets you replace it with some from another source. So carboxyhemoglobin, is going to release carbon dioxide because the hemoglobin wants to go out and bind oxygen, but that free carbon dioxide can continuously kind of fuel in and be released into the alveolus and exhaled out. But then we finally have our bicarbonate ions. When it comes to bicarbonate, once again, we have to convert it. So the bicarbonate will be picked up by the red blood cell. Now, in order to do this, the red blood cell gives up a chloride ion. It'll do that because it needs to maintain electrical neutrality. One negative charge in, one negative charge out. This phenomena is called a reverse chloride shift. Now that we have our bicarbonate within our cell, you can see the hemoglobin could free up some acid that it was buffering, and as the hemoglobin frees up the acid, as the bicarbonate enters the cell, they spontaneously come together to give you carbonic acid. Now that we have carbonic acid, carbonic anhydrase can do its job and convert that carbonic acid into water, and now we have carbon dioxide. And that can then diffuse in the plasma and be exhaled out. So like I said, this equation that you see here, series of equations, become critical to understanding how that conversion of carbon dioxide to bicarbonate and bicarbonate to carbon dioxide work. And you can see that playing out in the diagram we just took a look at. Let's take a very quick look here at internal respiration as well. Similar process here. First up, we'll talk about where we're exchanging gases between. Internal respiration is an exchange of gases between the tissues and also blood, so you see that. Direction of movement. Oxygen should move from blood into the tissue, carbon dioxide from the tissues and into blood. Therefore, the higher partial pressure of oxygen has to be in the blood, and the lower partial pressure of oxygen during internal respiration within the tissues. Higher partial pressure of carbon dioxide within the tissue, lower partial pressure of carbon dioxide within the blood, once again during internal respiration. Next, we just account for each manner of transport. If we look at plasma, the dissolved component of oxygen, you don't have to do any conversions. It just simply goes down that partial pressure gradient and will enter the tissue. When we consider oxyhemoglobin, well, things change here at the tissue level. Due to the metabolism of the tissues, the amount of oxygen will be lower, so the PO2 will decrease. The amount of carbon dioxide should be increased. The temperature and also the amount of acid should be elevated. In other words, hemoglobin's affinity for oxygen will be decreased. So oxyhemoglobin will begin to release hemoglobin and free it up. And once we have free hemoglobin, it can go down its partial pressure gradient and ultimately reach the tissues. Therefore, that's oxygen's story. Next, we'll deal with carbon dioxide. As carbon dioxide goes down that partial pressure gradient and enters blood, 7% of it will just stay in blood as dissolved, over and done with. Another 23% will continue to diffuse into red blood cells. Remember, hemoglobin is being freed up. Why? Because it's kicking off oxygen. So some of that freed up hemoglobin will begin to bind up carbon dioxide, becoming carbamino or carboxyhemoglobin. And of course, as it binds up carbon dioxide, it will release oxygen, so we get even more free oxygen to transport into the tissues. And finally, we would have bicarbonate ions. Remember, we have to convert carbon dioxide into bicarbonate. This once again would occur within the red blood cell. In this situation, we're going to run those reactions in the reverse direction, or from left to right. Carbon dioxide will be united with water by carbonic anhydrase to form carbonic acid. Carbonic acid will then spontaneously fall apart and give you bicarbonate and a hydrogen ion. The bicarbonate obviously doesn't stay within the red blood cell, so the red blood cell has to pump it out in the plasma. Once again, we see an exchange process play out. One negatively charged bicarbonate ion in the plasma, one negatively charged chloride into the red blood cell. This is called the chloride shift, and it plays out during internal respiration. Once again, this is all to maintain electrical neutrality. The acid that was produced as a result of this reaction will be picked up by hemoglobin. So hemoglobin not only can carry oxygen, it can not only carry carbon dioxide, but it can also help buffer. The buffering is provided by the amino acids within the globin molecules. The amino acids have the ability to pick up or release hydrogen depending upon the situation. And that's the story of internal respiration. Now I realize this can be kind of intimidating at first, but you have to take it step by step and account for all those little steps in order to get the overall picture. Alright. With that being said, we'll stop there with the process of internal and external respiration, and in the next lecture we'll talk about control of breathing or control of respiration.